Okay, so let's I hope you hear my voice, right? And able to see the slides as well.
Yes, ma'am.
Okay, so let's so I'm just going slightly beyond the syllabus. I mean, not beyond, but I'm taking a slight shift. Okay. Actually, I'm supposed to cover local search techniques, which I'm skipping for time being, and will cover it later. So I just wanted to start with the fourth component of the first module, which is the classifiers. Okay, and what we will see today is the naive-Bayes classifier using normal density function, and we will see some implementation of whatever we discussed today in Python. Okay, so we need not worry about how Python does this. Even if you do not know the Python programming, it's fine. Okay, this is just to understand what we do, or when we are given a tool, what they exactly do inside. Okay, so that is the insight that I wanted to give. Okay, but I'm not sure if I will be able to cover this in 1 hour. If not, we will continue this in subsequent classes. Okay. Okay, so basically, what is classification problem? So now assume that, okay, there is a conveyor in which somebody is placing the fruits, okay, and you have a screen, you are here, okay, you are here, and the conveyor is beyond the screen, okay, behind this one, and you are unable to see this conveyor, okay, and but somebody is here, and this person is, whenever he is placing a fruit, he is asking you to guess what fruit is coming next. Okay, so suppose you are given the knowledge that there are only 2 fruits, either the banana or it is the jackfruit. Okay, so how do you classify now? Do you, so it's like I am you cannot see me now, okay, you just see the screen that I'm showing, but now I'm saying I'm picking a fruit in my hand, I'm asking you to guess, and I'm saying all the information that I have given you is only that I have only 2 fruits and I'll choose one of them at any time. Now, how could you guess what fruit I have chosen? Anyone?
Either a banana or the other fruit, ma'am.
Yeah, but what is the how? So when we say classification, we have to come up with a measure. Okay, so with this much confidence, I say that you have chosen this one. So it's kind of equal probability, right? Yes or no?
Yes,
So
ma'am.
we have equal chances of choosing either banana or jackfruit. Okay, so that's all we can do. And this is kind of a more static classification. Okay, so I mean, it's kind of a random guess. That's all we can do. We cannot do anything greater than that. Okay, and but basically, the classification problem don't leave us with this minimal information. Okay, so suppose if I say, okay, suppose if I say that I am conducting this experiment, that is, you do not see the conveyor, but somebody is placing the fruit on the conveyor and asking you to guess what fruit will come next. Okay, but you are given the information that we are conducting this experiment in summer, say May. In the month of, we are conducting this experiment in the month of May. Now, how do you do?
In the month of May, jackfruit is more available than
More
bananas, ma'am.
available, yes. Okay, so great, Sedaram. Okay, so this is the information that we have. Okay, since we know that it is summer, the occurrence of jackfruit might be high compared to the banana, because in May because this banana is available throughout, and if it is a special, okay, we would prefer to pick up that one, right? So we can say that if I know, okay, these are called prior knowledge. Okay, so how much quantity of the jackfruit could be available at that point of time? Okay, that will give you the prior information. Okay, and if we say omega 1 and omega 2 are the class labels, that is banana and jackfruit, say for example, my decision would be like this. Okay, if the prior probability of the jackfruit is high compared to the prior probability of banana, then I will decide for the jackfruit. Otherwise, I'll go for banana. Okay. Again, this would vary depending on the month. Okay, so we have slight variation in deciding how what fruit will come next. Okay, suppose if I say we conduct this experiment sometime in December, okay, might be that this probability could be more. Okay, so we have introduced probability in decision making. Okay, somehow we have some, see, in the earlier case it is a random guess. Okay, and we have nothing to do about that. Okay, now we have some information which is called the prior probability. Okay, and again, the classification problem don't leave us with only the prior probability information. It gives us some more information. Okay, so given a classification problem, basically we measure something called features. Okay, and just hold on. Okay, so we measure the features of the information that we wanted to classify. Okay, say for example, I am measuring the length and the width of the or the thickness of the fruit. Okay, so we will measure this for both the fruits. We will take many samples of jackfruit. I measure its length and thickness. Similarly, we take many bananas and measure the length and width of the banana. Okay, and that is called a feature space. Okay, see here the feature now. Okay, with a single fruit we have the length and the thickness. Okay, it is a vector. So remember that whatever we have seen with linear algebra holds good here. Okay, now we ask this question. Okay, what is the probability that the observation that we have made now belongs to this class omega 1? Okay, we say what is the probability that this fruit is a jackfruit, given that the length and width of the fruit is this one, this x. Okay, similarly we ask how much probability is there for this measurement to belong to a banana. Okay, so this is exactly the classification problem. Any doubt here? So this is the fundamental question that we are going to ask. This is the class label and this is the feature. Okay, so we say given this feature vector, what is the probability that it belongs to a particular class? Is this clear?
Yes, ma'am.
Okay, fine. Okay, now just we recall the law of total probability, which we have already seen with the probability. So there is a sample space and you have mutually exclusive partitions B1, B2, B3, etc. And and there is a event A, okay, and we want to find the probability of A. So we compute it by taking the intersection of that event with B1, B2 and B3. Okay, and this is what it is. And this intersection can be replaced with conditional probability and the prior probability. Okay, so when we say mutually exclusive, okay, now there are two cases. Okay, is this one mutually exclusive? So mutually exclusive means, okay, so the right hand side, is this mutually exclusive, the space?
Yes, ma'am.
Yes.
Can't understand, ma'am. Could you once again say that?
No, actually, when we say B1, B2, B3 are mutually exclusive, okay, so recall the same example that I gave you while we were seeing the probability question, okay. So I said, suppose if I measure the height and weight of the people, okay, and I wanted to say based on the height and weight, whether the particular person is a male or female or it is a kid. Okay, so if this is the classification there are three labels, male, female and kid, and I wanted to classify the measured feature which is the height and weight of a particular person, and I wanted to decide on the gender. Okay, so in this case we say that this B1, B2, B3 are mutually exclusive. Okay, mean to say that if I have a data with say height 5 feet and weight 40, I say that the same data cannot occur in the female set. That makes sense, right? See,
Yes, ma'am.
in reality, there could be both
possibilities,
men
ma'am.
and women with 5 feet and 40 kgs. Okay, but when you see from the machine point of view, we say that for a height of 5 feet and 40, I'm asking it to learn both the things. He is a male as well as she could be a female, okay, which is wrong. For us maybe it is okay, but for a machine we should give only clear instruction. Okay, so I cannot say exactly 5 comma 40 is both man and women. That I cannot say, but I can say with 5 feet and 1 inch and 40 is a male, and 5 feet and 40 kgs is female. That is okay. So in that case, the feature space will be something like this. Okay, it is not. This is mutually exclusive actually, in the sense that I am not saying the same data appear in both the sets. See, I cannot say the same value with two different. I mean, if I say 3 plus 5, I should get only 8. Okay, I can say input is 3 and 5, and I should get only 8. I cannot say it could be 8 or 7. That's the point that I wanted to make by mutually exclusive. Even if there are mutually exclusive data, okay, the good practice is to eliminate such data and allow, say for example, if there are more number of female with 5 feet and 40 kgs, then I should allow that value in female and remove whatever is there in the male set and make the data mutually exclusive. Okay, I cannot, something like this I cannot have. This is overlapping. Okay, I have the same data, I'm asking it to learn both triangle and dot, which is not possible for a machine. For the same input I cannot expect two different outputs, but this is okay. The inputs are different, although they are kind of interleaved and overlapping. This is fine. Is this clear?
Yes, ma'am.
Okay. Okay, so given this one, if there is a new sample that is coming, which is A, our event A is the new sample which we wanted to classify as a man or woman or a baby. Okay, in that case, I can, find out this one, probability of A given B1 into probability of B1. Okay, and I need not add them, but I can find these probabilities independently and say that A belongs to the class whichever is giving the maximum probability among these three. Okay, if this product is giving a maximum value, then I would label A as a class B1. Okay, and if this probability is high compared to this and this, then I would prefer to label A as B2 and so on. Is this okay? Okay, so this is the fundamental of classification. Okay, fine.
Yes, ma'am.
Okay. So for the Bayes theorem already we have seen. Just to recall, okay, so we know that A intersection B is equal to B intersection A in set theory, because this is commutative. The intersection is commutative. So if we take the probability of A intersection B, I can write it as conditional probabilities, like probability of A given B into probability of B. And this one we can write it as probability of B intersection A into probability of A. And since the left hand side are equal, I can equate the right hand side as well. So we are computing the probability of B given A, okay, in terms of probability of A given B into probability of B divided by this probability of A. That's what is given here. Okay, so now with classification we coin each of these terms some name. Okay, and this is called likelihood. Okay, how likely is this A to belong the class, I mean, what is given? So this is one class label. Okay, see in our classification problem, this is what we wanted to do. Okay, we are given, this is what we wanted to find out. Okay, we wanted to find a class label for the given feature. I wanted to find out what is this omega j. Okay, and we say the probability of x given omega j into probability of omega j divided by p of x. Okay, and how likely is this x can be generated from the model of omega j, or how likely that this x belong to the class omega j. That is the likelihood. Okay, and prior, how common this class is. Okay, that is the prior value. Okay, and evidence, why we name it as evidence? Because this is what we have observed. Okay, so in crime site and all, whatever they observe, that is the evidence, right? So the same terminology they use it here. Okay, this is the observation that we have made. Okay, and so that becomes the evidence. Okay, and this is called the posterior probability. Okay, so I mean, an interesting thing to observe here is, okay, see the term of posterior and the prior. Okay, and what do we have in prior? We have probability of the class, right? And what do we compute here? The probability of class given an observation. Can you see that? So here there is no condition on that. Okay, so this is a prior probability, and posterior we give additional. Okay, we wanted to find the probability of this class in the light of the feature x. Okay, so that is why it is called the posterior probability. Okay, I hope you remember that when we were discussing the conditional probability, the probability might increase. Okay, if this is a proper sample of this class, okay, this probability, posterior probability will increase. Okay, but keep in mind that we are trying to find the probability of the class in both the cases, prior and the posterior. Here, the whole picture, this is in the light of the observation that we have made. Okay, and what is the evidence? What is the probability of x? Okay, probability of x is how common this x is. Okay, and this is independent of all class. Okay, x could be any feature. Okay, so if there are only two classes, it is the sum of all observations that we have made from both the classes. Okay, so that is the probability of x. Okay, and for a classification problem, this is going to be a common factor because of this formulation. Okay, and we have, see, this p of x only acts as a scaling factor. That is the posterior to become a probability, only we have this p of x. For a classification problem, I need not have this as a probability. I'm I'm okay even if this, I can say, if the numerator of class 1 is greater than the numerator of class 2. I mean, instead of j, I'm saying 1 and 2. Okay, in that case, I'm happy to go with whichever class has yielded a bigger number for the numerator. Okay, so for classification, we just ignore this p of x. Is this clear? Any doubt? Am I with you?
Yes, ma'am. No doubts, ma'am.
Okay. Okay, now let's see what is discriminant function. Okay, so this is the general rule that we have seen. Okay, we have just generalized whatever we have seen in the second slide. we decide to class omega I if the prior probability of omega I is greater than probability of the class omega j for all I not equal to j. Okay. This I can write it as I can introduce some discriminant function in terms of the feature, and I can say whichever discriminant function, I mean the discriminant function is associated with the class. Okay, that is important. Okay. So if that is giving a higher value, then I can decide for that particular class I. Okay. Suppose if we say that the discriminant function is the posterior probability, okay, we simply substitute the posterior probability formula here. Okay, probability of omega j given x will be probability of x given omega j into probability of omega j divided by the p of x, which is actually this. Okay, and we have generalized to c number of classes. Okay, and you can see that whatever you have inside the summation is same as that of the numerator. Okay, but it sums for all the classes, all the samples in all the classes. Okay, and for classification, we simply ignore this denominator and we are happy to go with only the numerator. And did you observe that I have a small p here and there is a capital P? Is there any difference? This capital P is probability. Okay, it's a simple probability, but this is a probability distribution. Okay, when we denote with small p, it's a probability distribution. Okay, and I can take the log of these things. Okay, y log of these things. Any guess? Suppose if I take the log of this, we will get probability of log of p of x given omega j plus log of p of omega j. But any guess
For easy
why
calculation,
or?
instead of multiplication, we can go for addition, ma'am, by using
But we
log.
are doing an additional operation, right? We are applying log for two quantities.
Yes, ma'am.
So I
When
wouldn't
we use
say,
log, we can simply add, ma'am. But
yeah,
without
see,
that, we have to multiply both the values, ma'am.
yeah, Sedram, but my question is here I have only one multiplication, but here I have two logs and one addition, right? I have to,
That is the logarithmic rule, ma'am. Log
huh?
of m into n is equal to log. That is the
No,
log rule,
that
ma'am.
is okay.
Log
That
of
is
m.
okay. When you have mn, if you take the log,
Yes,
you
ma'am.
will have log m plus log n.
Log
That is
m plus
okay.
log n.
But but why should
Okay.
we do this? Why should we do this?
No ideas, ma'am.
No idea. Okay, great. No issues. Okay, but this is the kind of practical difficulty that we face. Okay, only because of that we perform this. Okay, what is that practical difficulty? This is these are all probabilities, right? So when you multiply probabilities, okay, see, although we have it like single numbers, if this feature, we have a vector, right? And when you multiply, you know that the probabilities are real numbers, right? And the value lies between 0 and 1, right? So when you multiply probabilities, and this is a simple probability, okay with it, but when you have a sequence, okay, you might need to multiply more probabilities, okay? So in that case, when you keep on multiplying real numbers, and that too which lies between 0 and 1, what happens? If you
We may
multiply,
get confused, ma'am.
see,
Or else results in zero, ma'am.
Yeah, okay, so that is the problem. The second one is the actual problem. Okay, see, we are not going to multiply, okay, for sure, we are not going to do any of this multiplication, okay, it is harder for us. We are allowing the machine to do, okay. So there is nothing like a hard or easy for machine, okay, everything is easy for it, okay. And when we multiply, say, zero point 0.5 and zero point 0.5, what do we get? We get 0.5 into 0.5 is
0.25.
0.25, right?
25, ma'am.
So, yeah, 0.25, is it greater than 0.5 or what?
It's less than 0.5, ma'am.
Less than 0.5. So if you multiply, then 0.25 into 0.5, it will keep on decreasing, right? And finally, it will be a number which cannot be represented by a computer. And we will lose the information if the sequence of multiplication is so long. Okay, so that is why we are going for log space. Okay, just to make sure that we do not lose information because of this multiplication. Okay, just it is the sake of implementation in a computer. Okay, so we go for the log space. I think this is clear.
Yes, ma'am. Clearly understood, ma'am.
Okay, thank you. Now, okay. Okay, so before going to this, okay, so let's stop it here. And let's see if it's quite some time that I have run all these things. Okay, let me clear. Should I go for this? Okay. Okay, so what usually researchers do, I hope you are able to see the screen, right? I don't know whether
Yes, ma'am.
I'm
Visible, ma'am.
very able to see the letters.
No, ma'am. Kindly zoom in. Yes, ma'am. Now it is visible, ma'am.
Okay, fine. Okay. So actually, if you take today's researchers, okay, given some data and you know some model, okay, whatever we have discussed so far, all models, okay. So each one of this is a model, we can say, although they are all equivalent, okay. They simply go and implement this one, and that's what exactly we are going to do now, and we will slowly build up our model, okay. So these import in Python is like your include, okay, hash include in C or C++, okay. So these are all packages that we include to perform something, okay. So these are all libraries, okay. Forget about this one, okay. So we will run this block, okay, so that all the libraries are included. Now we have the data. I don't know, should it take this much of time? Okay, so okay, so it has run. Okay, so this is Jupyter Notebook. Okay, and I mean, the convenience of using this is we can run this block by block. Okay, and once it is run, we will get a number like this. Okay, and these are all unrun blocks. Okay, now we have our data in some Excel sheet. Okay, and we are going to read it and see few data in the file. Okay, so that is the next block. So okay, so it has some data. Okay, and the labels, so it has X and Y, and it has a class label. Okay. Okay, this much is okay. Then we say, okay, there could be more than one class here, and we try to group it by class. And we are trying to plot each of the class, okay, with some markers. Okay, so let's run this and see. Okay, so this is what we have. Okay, so there are 4 class in this file. Okay, I mean each one gets a different color. Okay, but this is the class. Okay, so now from this, what is see, p of x is the probability of each of this one. Okay, each of these samples. Okay, and this is how the class are distributed. Okay. Okay, now what I have done, so this block, I'm just copying it. Okay, so I'm copying it as the train and test. Okay, I'm just splitting the first 2 things, okay, which is the x and y axis. Okay, see the x and y axis, we are those are the 2 features, right? So that will be the data feature. So I'm taking it as data in, and the output that I want is the class label. Okay, so that will be coming here. Okay, so this is the next block. Okay, so I have separated out the x and y, and the corresponding labels will be here. Okay, fine. Now what do I do? Okay, I am separating out each of the class. Okay, so that we can build models. Okay, I don't know whether I have it here. Let me see. It's quite very long time I took this. Okay, so if you see my lecture slide, okay, if you notice the um, title, okay, it says knife base. Okay, so there is a classifier called knife base classifier. Now I have the data with me, and what I'm trying to do is apply the knife base classifier and see what happens. Okay, so I have separated out each of the class. Now I'll have only class A here, I'll have only class B here, similarly I'll have class C and class D. Okay, now what do? We separate out the input output in each of the class. Okay, and there is something called train test split. Okay, which will okay, so okay, I didn't say this, right? So whenever you have a classification problem, okay, if you are doing some project or a research with classification, suppose if you have 100 data. Okay, let me not say the count. Okay, I will say from by proportion. Okay, you have some amount of data with you, and to build the model. Okay, we will always have. See, these are all data driven. Machine learning algorithms are all data driven. Okay, so we will split the data as training data and testing data. Okay, in the percentage of 70-30. Okay, and we will be learning the information whatever we wanted to learn to classify from the training. Okay, this test will not appear in our training. The model that we develop for classification will not have any idea on the test data, because we have separated out the test data in the very beginning, and we are trying to characterize the test data using the representatives in the training data. Okay, so 70% of the data will come. So you can give the proportion. Okay, sometimes people would prefer to give 70-30, or it is 80-20. It depends. Okay, and remaining 30 will be treated as the test data. Okay, so that is what we are doing here. We are separating out from each of the classes 70% of the data for for training and remaining 30 for testing. Okay, so that's what we have done. And now I am putting all the test data together, because test data, although I know the label, I am keeping the feature separately. This is the known output. I know this is the label corresponding to this, but I should test whether the model that I have built will also give the same label. Okay, given the feature from this one. Okay, so we have combined all the samples from all the classes. Okay, for test. Okay, similarly, we do it for the training. Okay, okay, with both in and out. Okay, now if you take the shape of this, okay, see here. So totally there are 2000 data. Okay, 1400 samples, each having X and Y feature, is considered as the training data, and 600 samples, each with X and Y feature, is considered as test data. Okay, now this is what the researchers do. Okay, now I have the data. Now we will build something called nine. This will be given. Okay, there are many tools, and Python supports naive-Bayes classifier, and this is how I am supposed to use it. Okay, I create an object for this, and I ask the naive-Bayes classifier to fit the trained data. Okay, and this is the input, training input, and this is the training output. Okay, what do I say? For each of this training input, this is the corresponding output. Okay, I'm mapping that. Okay, and I'm asking it to learn. Okay, so this fit is the function which will learn the patterns available in this training for the corresponding output. Okay, and once it has studied, okay, so this is the testing that we do. Okay, with the model that it has developed. Okay, I'm asking it to test the model on the test data. Okay, see here we don't give the output here. I'm giving only the XY feature. Okay, the output label we are not supplying during testing. Okay, and the model will give you the label. That is the output. Okay, and we say that this is the prediction from the model. Okay, and what we do, we actually test predict equal to test in of. Okay, so we are going to concatenate the X and Y feature of the input in test and their corresponding labels, okay, which is test predict, okay, as the third column, which is the class. Okay, so we will have now three. Okay, along with the XY, we have the class labels which are predicted by this model. Okay, we are passing this variable. Okay, the test predict. Okay, now we are trying to. We should know how good is this model is, right? So what do? We simply count how many misclassifications are there. Okay, we say, see, this is the label that I have got for this particular input. Okay, and is it the same as that of this test output that I already have? Okay, we have here, right, the test output. So that out, if these both are same, okay, there is no problem. If there is a mismatch between what is predicted and what we have as a ground truth, okay, then it will be counted. Is this clear? Is this clear?
Yes, ma'am.
Okay. Okay, so now let's see what happens. We'll run this. Okay, so it gives some warning, but still it runs. Okay, and it gives 0. Okay, that is the count is giving me 0. Okay, that means that there is no mismatch. That means that all my data are correctly classified. I'm happy. I'll go and write a paper. Okay, and try to publish, but I will not know what is the insight of that. Okay, so suppose when we submit the paper without any insight, the reviewer will ask you some questions and we will come back and find out. Okay, so we have used uh, an object, right? So we'll try to find out what are all the things that are associated with that object. Okay, and let's see. Okay, it's giving me some numbers. Okay, it's giving me some numbers, but what is it? Okay, we do not know. Okay, so here there is something called theta. Okay, which is this one. Okay, till here is the theta. This is sigma. Okay, and these are prior. Okay, and it says class prior. So let's try to associate this with what we have. Okay, so since it is clearly saying it is prior, what is it? It is the class prior. We already saw that when we plotted the data. How many classes are there? We have 4 classes, right? And each class will have a prior, right? So that it says it is 0.25. But how do you find the prior as 0.25? Still it is unknown to us. Okay, and the theta and sigma. Okay, so let's see what it is. Okay, so it will be very blank, and most of you, when you do the project for final year, this is how you do, and you will not be able to answer any of the question that is posted based on the, you know, the model. Okay, so we'll see some more theory and come back. Okay. Okay, so now what we are going to do is that, okay, so now let's assume that, okay, see when we see the, so I said this is probability and this is probability distribution, right? So what is probability distribution? I know the class label. I take many, jackfruit and measure their length and thickness. And similarly, I know that it is banana and I measure this x. Okay, and if when we plot this, you know, P of x given omega j and x along the, the feature along the x direction, and along the y direction you have this P of x given omega j. Okay, you will get a function. Okay, so that is this, the probability distribution. Okay, so let's not go into detail of that. Okay, and suppose if that distribution, okay, is assumed to be this one. Okay, we will assume that the data is normally distributed. Okay, and there is something called multivariate. What is multivariate? If there is a multivariate, there is some, multi means many, right? So there should be like one. Okay, there is something called univariate and multivariate. Do you know the difference? What is the formula for normal density? I think we have already seen when we were seeing the probability, right? When we saw the probability distribution function, we saw univariate normal density or univariate Gaussian distribution. You remember?
Yes, ma'am. It is summation of XA and PA, ma'am.
Summation of xi, no, for normal density you will have 1 by root of 2 pi. Do you remember that? You have 1 by root of 2 pi, and then you will have a small sigma. This is also something like this, okay? Root of 2 pi here. Instead of this, you will have this. And here you will have x minus mu divided by x minus mu divided by sigma. I mean, this minus half will be there, but you will have x minus mu divided by sigma the whole square. Okay, so that is the formula for univariate. Okay, univariate means the data that you consider is a is what is scalar data. Okay, this x, okay, the x that you are considering is scalar, means that each feature is a single valued feature. Okay, in that case we call that as a univariate. Okay, that is the dimension of the data that you consider as single in univariate, and in multivariate you will have d-dimensional data. Okay, and because of this dimension, see, this normal density is a bell shaped curve. Okay, and this will be, since we have now d dimension, if you see from any of the d dimension, everywhere you should see this bell. Okay, and that's how the same thing, the same formula, 1 by 2 pi. See, when we have scalar, this d is 1, right? So we have 1 by d and 1 by 2, and this will be square root of that one. Okay, now since we have d, we have 2 pi d by 2, power d by 2. Okay, and instead of variance or standard deviation sigma, okay, now we have something called covariance matrix. Okay, let's see how we compute here. Okay, and this x is the feature, okay, and mu is the mean. Again, this is the inverse of covariance matrix. Okay, so if x is this one, the feature vector with observation 1 and observation 2, okay, and the data set has n data, you will compute the mean of the data like this. Okay, mean is nothing but the expectation of x. Okay, which you can distribute like expectation on the observation 1 and the observation 2. Okay, so this you can say it is mu 0 o1 and this is mu o2. And how do you compute this? So suppose if this is a vector and I say, when I say dot O1, this is not multiplication. I am simply referring to the first feature of xi. Okay, I sum all O1s of each of the xi for all the n samples and divide it by 1 by n. Okay, normal average of this O1. Similarly, I'll find the average of O2 for all x's. And there are, since there are n samples, I'll divide by n, and thereby we will get a feature vector. Okay, mu is now a feature vector with these two components. Is this clear? Is this okay? Can you understand that this mu is a vector?
Ma'am, could you please repeat the second and third one, ma'am? X and mu once again, ma'am.
Okay. So now what we say is that when we say multivariate data, the dimension of the data is more than 1. In that case, we will say that it is multivariate data. Okay, and we take, for example, the dimension of x is 2. Okay, we have x is a vector now with dimension 2, 1 by 2 or 2 by 1, whatever you say. Okay, so you have feature 1, this is feature 2. Both these feature together form a single sample x, and there are n such data. This xi, I have x1, x2, x3, etc. up to n, xn. Okay, and each x will have two components in it. Okay, now how do you find the mean of these samples, mean of this x? Okay, mean is, we know that, see, if we are given some simple scalar value, we know how to compute the mean, right? Suppose if I say the data you have is say 3 and you have 2 and you have 5. Okay, only you have 3 samples. If I ask you to find the mean of these 3 numbers, what do? You just add these 3 numbers, right, and divide by how much?
3, ma'am.
3, right? So the same thing we are doing for independent feature. Okay, so this is nothing but the expectation of x, the mean of, I mean, mu is the mean of the entire sample in D, okay, which is nothing but the expectation on x, which is the expectation of the feature 1 and the expectation of feature 2. And we represent this E of O1 as mu O1 and this expectation of O2 as mu O2. And this is nothing but I sum up all O1s of all x's in D and divided by, since there are n different samples, I divide by 1 by n. And similarly, I add up all O2, observation 2, O2s for all n samples and divide by n. So I'll get a mean vector. This is one number, this is another number. This is mean of O1 and this is mean of O2. Is this clear?
Yes, ma'am. Now clear, ma'am.
Okay. Now similarly, you will find the covariance. So since we have a vector, instead of variance, we will have covariance. Okay. Which is nothing but the same thing, variance. So along the diagonal, you have only the variance. Expectation of O1 minus mu O1 the whole square. Okay, so this is the variance of O1. This is variance of O2. Okay, and you know how to do the expectation now. Okay, the same thing. This is how you do the expectation. And when you have O1 minus mu O1, what do you do? Instead of x, you have this one, right? So you will do this. I will have xi dot o1 minus mu o1. You will do this. You will apply the same formula, and inside the summation you will apply this one. Okay, for each of the x you will consider o1. This will be common for all o1. Okay, and you will divide by 1 by n minus 1 because this is first order moment, right? And this variance is second order moment. Okay, so it's okay. Okay, if you divide by 1 by m, that is also fine. But the accurate one is to go with 1 by n minus 1. So diagonal is no problem. Okay, it's a simple variance. And the off diagonal elements give you the covariance. Okay, how this feature varies with this feature. Okay, so it is expectation of O1 minus mu O1 into O2 minus mu O2. Okay, the same thing is up in, so it's a symmetric one. Okay, all the covariance matrices are symmetric in nature. Do you see that? I mean, if you multiply it this way or the other way, it's going to be one and the same.
Yes, ma'am.
Okay, so this is covariance matrix. Okay, so let me stop here because if I start this one, this will drag. Okay, so let's continue this tomorrow, but don't forget all these things. Okay. So let's so using this we will go and check in the code what these things are, and then we will continue tomorrow. Is that fine? I'm yet to prepare the dinner.
Yes, ma'am. It's fine, ma'am.
Okay,
We'll
thank
continue
you.
tomorrow, ma'am. Thank you, ma'am.
Oh, thank you, thank you.